So that's it, that's the same, right?
You will consider examples in the core holder and supply that to the top. And your liquid will go through. So that's it.
But what are you going to be measuring? What are you going to, the volume?
Time. Yeah.
Oh, okay, so there will be timing, and saturation is originally known, right? Because the porosity of the plug is known,
Yeah.
so the amount of water is known, right?
So you wait for all liquid to go through.
To drain and how long it takes, right?
Yeah.
Okay, and at each particular time you will know how much liquid you expelled. That means you will know how much saturation is left in the pore, right?
So
Okay.
it's probably going to be like quick time.
Yes.
And at least it's going to be empty. So that's
After, in the end,
all the gas.
all the air is going to expel all the water from the pore. So the outcome of that experiment is two curves. You'll be collecting dots, data points, okay? And it won't be as nice as this. This is theoretical and ideal, because there's a lot of sources of error, and keeping track of your sources of error and how much error they will introduce into your measurements is also part of the job in a lab experiment. So when you read your manuals before you come to class, it'll make sense to kind of try and think ahead and try to figure out where the error will hide and how much it might contribute to your, because your points will be like. But you know from theory, because you'll be taking petrophysics at the same time, that your curve should be looking like this, okay? So this is that. Now, why this is important, why relative perm is important? For the same reasons I pointed out when I was talking about absolute permeability. The reason being, this is the stuff that goes as input information to any reservoir model. When you do reservoir simulation, you will be using this a lot. And in your senior year, you will be doing reservoir simulation exercise. There will be a whole course titled Numerical Reservoir Simulation, where you'll be typing in, from tabulated data, you will be typing in these dots and getting these curves to tell the machine how to simulate your reservoir. Because this change in saturation corresponds to time. Saturations change over time as you drain the reservoir. So the machine needs to know, okay, if I'm here in time, like 10 years from the start of production, what should my permeability be? Well, if the machine has these curves, we'll just go, oh, okay, this is my permeability. And permeability will be calculated in the flow, we'll be using the flow equations in the simulator. And flow is what we're producing, okay? Volume of crude we're producing over time. So that's that experiment. Should we talk about API gravity first? Saturation, yes, okay. Since we already started talking about saturation, now, see how you're going to be needing saturations for this experiment. Now, how do you calculate saturation? How do you measure it? Saturation is another experiment in this lab class. And I believe at this point we're only doing like one. We used to do 2 tests of saturations using 2 different apparatuses. Now we only use this one here. It's called the Dean Starks apparatus. There's a bunch of videos on YouTube. It's used in chemistry and it's used in petroleum laboratories as well to calculate saturations. What happens here is you get a core plug of known porosity, which you can measure in that apparatus there, right? Known porosity. And you put it in a liquid in a vacuum chamber, and that liquid is soaked into the pores, and then you take it out. But how do you know the saturation? How do you know what volume, what part of the pore volume got saturated with the fluid, with the liquid? Water in this case, right? Because we're using, no?
Water
And oil. Oh, for this one we're going to be using water and oil. Because remember how when I talk about saturation is saturation of oil plus water saturation plus gas saturation. Because you will have all of them, all the 3 of them in a reservoir. Okay? So a plug will be saturated for you, I guess, by a TA. with oil and water, and the gas will be air, okay? So the trick here will be to figure out which fractions or what saturations each of the fluid has, okay? So what happens in this experiment is the core plug saturated with all the three is put in the Dean-Stark's apparatus. Boiling at the bottom is a hydrocarbon solvent, toluene in this case. Toluene is the most common solvent, hydrocarbon solvent used in Dean-Stark's experiment, okay? Toluene has a boiling point that is higher than the boiling point of water, but lower than the boiling point of the oil in the core. So, who can tell me what will happen with the water without toluene boiling down there? What will happen to the water in the rock sample, in the pores? Exactly. It will start boiling, meaning evaporating. It will start raising up that little L tube, okay? And because the temperature goes down there, it will become condensed, and it will pour down this water collector, which is graduated for you guys to keep track of the volume. This is not something that happens fast. It needs to be checked upon every 30 minutes over a period of how many hours? 1 day, 24 hours. Who's going to do it overnight?
In the beginning.
Oh, just in the beginning. Oh, okay.
And after 1
Okay.
day is going to be over.
So, after 1 day, all the water will be gone and collected. And you already know the pore volume, and that's the first known variable that you will get, the volume of water, and then you can calculate water saturation, okay? The fraction of the volume occupied by water, because by collecting that water, you will know the volume of the water, okay? What happens then is, what happens to toluene, it also boils and evaporates, but it doesn't do anything to oil, right? Because the boiling point is much higher. So oil stays trapped in the pores. So when the toluene, after evaporating, when it condenses up in the top, it drops back down, right? So it just keeps boiling and going down, boiling and going down. So the oil stays in there. But then there's a volumetric calculation that can let you know the volume of oil once all the water is gone. There's a formula in the manual that you will use, which is basically a simple volumetric calculation. Once you know this and that, you can take 1 and subtract SO and subtract SW to get SG. And that is what this experiment is about. Saturations. Okay? Dean-Stark apparatus is the key word. There's a whole bunch of YouTube videos about it. Oops. Okay, API gravity is a measure of oil density. By the way, saturations also go into reservoir simulation models. This is not just some geeky lab stuff that you just want to do for the sake of the experiment. No, this is all applicable, valuable information that oil and gas companies, operators, pay labs to do. Okay? So that their engineers have input information into their models. Okay. Now, API gravity is also an experiment. And as you remember from the lectures, API gravity is a measure of oil density. Okay? The formula is 141.5 divided by specific gravity minus 131.5. The way this equation is designed is to give water an API gravity of 10, nice and round number. Anything that is lighter than water will have a greater API gravity. Specific gravity is also a measure of density, and it's just density of oil divided by density of water. And consistent units gives you a fraction of 1. Engineers like fractions of 1 dimensionless because it's just easier to work with. Okay? So the way specific gravity works, the greater the specific gravity, the heavier the fluid. the greater API gravity is, the lighter the fluid. Bakken crude has like 41, I think, degrees API.